Hello everyone, I'm V Bhumika. I'm here to present a topic of power generation of wind PV battery based hybrid energy system for standalone AC microgrid applications. Here is the abstract of our project. In this article, we describe the power generation of wind PV and battery based hybrid energy systems for standalone AC microgrid applications. There are many results for resolving issues with the supply of electrical power, particularly in rural places where electrical networks are difficult to access. The usage of networks that are not linked to electrical systems allows for the provision of electricity to remote places, which is one of for determining this issue. They are denoted to as standalone microgrid systems. The standalone microgrid has its source of electricity addition with an energy storage system. They are utilized where power transmission and distribution from a major centralized energy source is too far and costly to operate. In this article, a standalone AC microgrid scheme with a hybrid power system comprised of wind, photovoltaic, that is nothing but solar cell, and batteries are designed and managed. So here is the introduction of our project. Nowadays, electricity plays an energetic role where we use it for lighting, heating, refrigerating, operating computer appliances, etc. For less emission of gases while producing energy, when it allocating energy to different energy generation systems, renewables such as PV, wind, and storage device maintain a crucial role because of the inclusion of variable non-conventional energy resources. When running in standalone mode, it requires various techniques for continuous and systematic power transfer. In this article, the author Sinha and Chandal presented a review of recent trends in optimization techniques for solar, photovoltaic, wind-based hybrid energy systems. They introduced the methodology in which different methods were used for the optimization of hybrid-based non-conventional energy resources. They used different algorithms which include optimization, including hybrid algorithms. This generation used artificial intelligence algorithms as they have better precision and good convergence. So finally, they decided that different procedures have different accuracy and precision level. And also there is a difference in convergence speed. So the choice of an algorithm or methodology may vary with user requirements. And in one of the article which is introduced by Bahramara and Mogadam and Hafifam, like optimal planning of hybrid renewable energy system using Homer software. They proposed an article about the ideal planning of hybrid renewable power sources. They used the Homer software, which is defined as hybrid optimization model for an electrical renewable software system, which was developed by the National Renewable Energy Laboratory. They determined that more than grid connected mode, HRES modeled in standalone mode. In this project, we are going to present the power generation of wind PV battery based hybrid energy system for standalone AC microgrid applications. So here is a view on hybrid energy power generation, which shows a block diagram of it. So the block diagram represents hybrid energy generation station, and it includes PV, solar cells, wind energy, battery, and inverter. It tells that the solar cell, wind, and battery are the inputs that generate some energy and pass it to the inverter. The inverter stores the energy and sends that energy to the load. As we are seeing a DC bus over there, it is also identified as the DC link, which serves as an interface between the AC to DC converter and inverter. The proposed system is going to generate the power using non-conventional energy resources that are shown below. So here is a solar cell or PV cell. So solar or PV generation of power is the procedure of converting radiant energy from the sun into electricity using solar panels. Solar panels, also called PV panels, PV systems can to be installed in grid connected or off-grid configurations, which is also known as standalone mode. The figure below demonstrates how the PV cell is linked to the DC bus, then to the DC to AC converter, and also known as an inverter and ultimately to the load. So here, first PV model generates the power in the form of DC and then it passes to the converter. That converter converts the DC power to the AC and it sends it to the load. So here is a wind generation model. By transforming the kinetic energy of moving air into electricity, wind energy is cashed off to generate power. The wind moves the rotor blades of modern wind turbines, changing moving energy into rotational energy. This rotational energy is then converted into electrical energy with the support of a generator. That figure depicts the production of electricity utilizing wind energy. And in this diagram, the generated power is routed through converter 1 and AC to DC converter and through converter 2, which is also DC to AC converter and also identified as an inverter with the head of the DC bus. The line between the rectifier and inverter is known as DC bus or DC link, and the output of the inverter is linked to the load in AC. So here is the battery system model. The battery is completed up of a DC to DC boost converter and a nickel. It is made up of nickel metal hydride battery through the PI controller. This converter is in charge of maintaining the DC bus voltage. The energy storage device and DC to DC converter are shown in the figure below, which explains how the energy is kept in the battery and transferred to the inverter with the aid of a boost converter. A boost converter creates a DC output voltage that is larger than the DC input voltage. It is obvious from the name alone that this is a boost converter used for DC voltage step up. The inverter's AC output was sent to the load. So here is a load side model. As conventional resources are depleting, we are using non-conventional resources for the generation of energy. But in most cases, non-conventional energy resources are generating DC, while conventional or non-renewable resources have adopted the AC system. So this imperfection between the two systems requires an inverter for converting the DC supply to the AC supply to fulfill the load demand. Combining of solar cell and wind when connected to grid can help in reduction of maintenance cost and increasing reliability of renewable power while supplying to load inverter output voltage. This figure shows a load side model in which all the hybrid resources give DC power with the support of an inverter, and inverter changes that to AC power and send it to the load. So here is a control scheme which includes PV, wind, and also to the inverter side. So in this section, we are going to present and control of PV module. In this section, there are different controlling techniques which are going to discuss below. There are control of the PV, control of the wind MPPT, battery or electrolyzer controller, and control of the inverter. The figure below shows the control of the PV cell from which can say that the irradiance block is associated to the insulation to current gain. And also there is a current variable of the PV model which is denoted by IPV. After saturation, the product of IPV and irradiance gives PPV. Now the production of insulation to the current gain block and IPV is solved, thereby it is coupled to VPV block. And there are bus creation block decreases the number of lines needed to route signals from one area of a diagram to another by combining a group of signals into a bus. The production of the regulated voltage source is associated to the current measurement, which is then connected to the PV positive through a series RLC branch, and the VPV is linked to the source. The PPV is associated to the go-to block, which without really connecting them, transfer its inputs to the other blocks, whose inputs can either be real or complicated. So here is the wind MPPT control. MPPT is nothing but maximum power point tracking, or which is a controller or regulator that must be utilized to operate the helicopter. These MPPT controllers monitor the determined power under several wind situations. Consequently, variable speed management of wind turbine generator system has been created to find the greatest output power with every change in wind speed. We are well aware that the rotor blades in the wind converting moving energy into rotational energy. Moving energy is nothing but kinetic energy, and which is that generates that generator terminals are used to transform rotational energy into electrical energy. From the figure below, the WM block is associated with the square math function Then the result of the math function and some constant value are the input to the product block. The output of the product block is coupled to the subtract, and then after saturation, it is associated to the output port TRF. Like the output port TRF, T reference is now input to the subsystem, which involves the product base stock block, as made known in which is figure in below. And this subsystems is coupled to a discrete first order filter, then to a current controller, and finally to a generator terminal. So here is a battery or electrolyzer control. A battery or electrolyzer control is represented in figure below, where a constant value and DC voltage input are distributed to the summation point before being coupled to a discrete PI controller, conferring to the form of feedback. The discrete PI controller block calculates the control signal using the backward Euler discretization method, which is a commonly used method in control systems for the correction of error between the command set point and the actual value. The relay is now connected to the discrete PI controller block by the summation point, and the data type conversion, which is Boolean, is attached after that. So here is the inverter control. The figure below shows the controller of the inverter is in three phases. The variable A, B, and C is associated to phase blocks and then connected to multiplexers, and also connected to RMS discrete blocks, now connected to phase RMS voltage blocks and line-to-line voltage blocks, and then connected to DC discrete PWM generator, thus to generate some pulses over it. So here is the output voltage and current of solar cell, which figure in the figure below. So it defines solar panel output voltage and solar panel output current respectively. From the figure below, we can see that there is an output voltage that rises maximum up to 880 volts, and then it is decreased to 655.8 volts. So here is the output voltage and current of battery and wind. The figure which are represented below are the wind output current and voltage, battery output voltage and battery output current respectively. So from the figure wind output voltage and current, the voltage is nearly to 260 volts and current is from minus 22 plus 20 amperes. So and from the figure battery output voltage, the voltage is constant around 660 nearly. So here is the input and output voltage and current of inverter. It shows the figure below shows the inverter input voltage, inverter output voltage, and current respectively. From the figure below, we can see that x-axis represents the input voltage of an inverter, and y-axis shows the time in seconds. So it maintains constant voltage DC from 0 to 1 second. From the one of the figure below, which represent inverter output voltage, there is a constant output voltage which is varies from -1 to +1 volts with respect to time, which is in seconds. So here comes to a conclusion, which paper proposes control techniques for power generation of wind PV battery based hybrid system for standalone AC microgrid applications. The proposed techniques introduced power management under variable conditions like solar irradiance and about wind speed variations, where the generation of power is used for standalone AC microgrid applications. And thank you.